So, we are now going to start with module 1. I am going to start with the first segment, and this segment I am going to title it a box of chocolates. We will see what the box of chocolates is about shortly. So, here is the plan for the segment. We are going to talk about a crooked confectioner. His goal is to sell as many chocolates as he can, and your goal is to basically just get the chocolate that you want, not buy all the chocolates that the confectioner is trying to sell you. Okay. So, the problem is what we will see is that it is hard to fight against this crooked confectioner, except if you use a random strategy, okay? And that is what we are going to see. It is going to be a very simple setting, but I want this to be a way to illustrate the power of randomization and also point out the need for a formal understanding of randomization, probability theory in the context of computer science. Okay, that is the very goal of this course, and this segment is just to illustrate the importance of this area. So, without further ado, let us see what is in the box. Well, we have 100 chocolates, 50 with nuts and 50 without nuts. Okay, that is the situation. Okay. The thing is this, you only want one chocolate is all you want, you are health conscious, but you want a chocolate with nuts in it. Okay. You do not want chocolates without nuts in it. Okay. But the confectioner, what he has done is, knowing the situation, he has wrapped up all the chocolates. So, you cannot see what is inside each chocolate. So, what you are supposed to do is come up with a strategy to get the first nutty chocolate, and that is it. Okay. And so, this is so the confectioner's goal, on the other hand, is to try and sell you as many chocolates as possible, because the moment you unwrap a chocolate, you bought it. So, all right. So, this is the situation. So, just in case you are getting a little worried whether this whole course is going to be about chocolates, let us actually see a little bit more of a computer sciencey application for the exact same scenario. Okay. So, you have let us say a data center, you have 100 servers in this data center, and now a new job arrives. It could be a web request, it could be whatever, a request for running a program, and there are some 50 servers that have capacities within them to run your program. The problem is you do not know which ones, okay? And you want to, in each attempt to put your program in a particular server is going to cost you some money. So, if you are going to repeatedly keep trying those servers that do not have enough capacity, you are spending a lot of effort. Okay. So, it is in your interest to find a server that has the capacity to run your program. Okay. So, this, if you can think about it, is exactly the box of chocolates problem, just rephrased in a language that is more amenable to computer scientists. So, what do? And this is what you typically do if you come from an undergraduate algorithms course, typical algorithms course. I mean, some algorithms course are covering some new topics, so that is great, but a typical undergraduate algorithms course would have taught you deterministic algorithms. And here is what you would do, you would pick chocolates in some arbitrary sequence, okay? Unwrap them one by one, check if it is nutty or not, and then keep repeating it until you find the first nutty chocolate. What is the problem with this? Well, the worst case is very bad. You can check 50 different chocolates and only succeed, you are only guaranteed to succeed on the 51st pick, right. This is your entire algorithms course, right. You learned how to come up with algorithms that in the worst case do gives good worst case guarantees, and this is the best worst case guarantee you can have. Okay. Can we do any better at all? If we insist on deterministic algorithms, of course, there is no other way, because this is a very simple argument, right. So, now all you have to do as a member, now this is a two-player game, you can think of it, between you and the confectioner. All the confectioner has to do is understand the sequence at which you pick the chocolates, and therefore, just place all the non-nutty chocolates first in whatever sequence you pick, and then you are then forced to pick 50 non-nutty chocolates before you get the first nutty chocolate. Okay. This is where the problem lies. So, the obvious question is, can we foil the scheming confectioner? How do we do that? Well, this is where we need to approach this problem in a slightly different way. Okay. So, whatever you learned in the undergraduate algorithms course, we need to not necessarily unlearn them, but add some tools to it, and that is in particular we want to try something beyond deterministic algorithms. We want to do a randomized algorithm. Okay. So, here is the algorithm, randomized algorithm. While nutty chocolate not found, buy a random chocolate and unwrap. So, this is the simple algorithm. Is it any better? That is the question. By now, any reasonable person would have a vague sense that it is better, but let us see. So, let us try to understand this issue. First, we will ask a wrong question, okay? Because sometimes to appreciate something, you first have to ask the wrong question and then slowly work your way to asking the right question. Can this randomized algorithm possibly take 51 iterations? If you are talking about possibility, yes, it can actually take 51 iterations, but this is missing the point. Okay, so, let us try to rephrase the question. Okay. We'll how likely is it that this algorithm will take 51 iterations? There was some mathematical jargon thrown at me just now, but given this is the first lecture, first segment of the first module, let us just go with something we know. Okay. We know it is very unlikely, that is all we know for now. We do not know how unlikely, right, that is something we need to figure out, right. So, this is that is really, so we have kind of reached the situation where we think we have a right solution. Given the level of information we have heard so far, we have come up with an algorithm that we know will fail, will do the bad thing, basically run for too long with very low likelihood. That much alone we know. Okay. But we need to this intellectual dissatisfaction, right, because we do not know what is likelihood. We do not know, when you say very unlikely, we do not know what that means, right. So, so the important thing is, can it be quantified? Can we put a number to this, and can we, if we have two possibilities that are, one is somewhat unlikely and and the other one is very unlikely, we want to be able to know how different they are, and we want to be able to compare, quantify them. And then the other thing is, we also want to understand whether these, what is so special about randomization? Would it, do sequential algorithms also have the same benefits? Why do they not have those benefits? That is another philosophical question that might rankle you. For now, what we have understood so far is that, there are ways to overcome these sort of pesky situations, but we need the right tools. In particular, what we are of course going towards is the probabilistic analysis tools to formally and quantifiably address this vague notion of likelihood. Everybody has this notion of likelihood. The gamblers in in 16th century had the notion of likelihood, right, but it took about 400 years to formalize this, and a lot of probability courses will just jump to the formalisms, but I want you to take a small take some time to realize that it took about 400 years. The first attempt at probability theory was in the 16th century, at least that we know of, and if enough material from Indian history was present, we might be even able to find out that India invented probability theory, but we do not have that evidence. So, a lot of things were invented here which we do not know about, right. So, but then we have clear evidence that it was invented there were attempts in the 16th century, but what we are going to talk about in the next segment is how Kolmogorov formalized this notion and helped us appreciate this vagueness. He gave a very concrete way to approach this vague notion of likelihood. Okay. So, that is going to be the topic for our next lecture. I have mentioned pretty much all the concluding remarks already, so I will quickly mention them. We need to move away from worst case analysis. We need to add some more realistic ways to approach algorithm design, and we need to be able to come up with formal ways to understand and appreciate it, and so that someone can trust our claims. So, it has to be formally and proved, trust that the desired outcomes is sufficiently likely, and we have to do this in a very rigorous manner, and we need the right mathematical ideas. That is going to be the topic of this course. And of course, as I mentioned, the fun fact is that what we are going to study is something invented by gamblers. So, the next segment will be an axiomatic approach to probability theory. This is the formal way to approach probability theory. Okay, that will be covered in the next segment. So, thank you.